Hi, this is Valentina Angelova for Computer Science 480, and this is my implementation of the 8 puzzle problem using the 6 different algorithms. I'll begin by running my code. So as you can see, a simple user interface will run the easy problem with breadth first search. We'll come back with our goal state in 5 moves, and here's the sequence of moves. Go to run a medium problem. Depth first search, that one actually took quite a bit of moves, so not ideal, or at least performs worse than breadth first search. If we run one of the hard problems, you'll notice that these do take a little bit longer, so this is the hard problem with A-star search counting the tiles out of place. Came back in 30 moves, and here's the sequence of moves to get to that state. As far as my implementation is concerned, I used a puzzle interface that my 8 puzzle implements, and it has a pretty simple set of methods for the implementation. Here is the 8 puzzle. I use an enumeration for the moves. The constructor takes in an integer array, so I modeled my puzzle as a one-dimensional 9-element integer array. I have functions for moving up, right, left, and down, which are pretty simple. Basically, for example, if we're moving right, and we're on the right edge, which are positions 2, 5, and 8 in the puzzle, then we can't move any further. Otherwise, we just increment the position by 1, switch to 0 position tile with the new one that we found, and return a new puzzle. In here I also have the algorithm or the heuristic implementations. So for the tiles out of place, I simply compare the current state board to the goal state, and if their values are not the same at the index, I increment a counter. For the Manhattan distance, I am looking at the column and row position of each tile and comparing it to the column and row position in the goal puzzle board. And then by taking the absolute value of the difference, I know how many positions I need to move to the left or right and how many positions I need to move up and down. And then I simply aggregate the number of positions that are required to move. So this is the puzzle. For the search, I actually used an abstract class since I wanted to keep a lot of the logic in here and then simply change the implementation of the queues. So as you can see here, I'm using pretty much the algorithm that's shown in the book. We take in a puzzle that we're going to solve, we create the first node, we check if it's the solution or if it's the goal, and if it is, we return a solution. Otherwise, we add it to the queue and then search. So in here, as you can see, I have 3 abstract methods. That's enqueue, dequeue, and checking if the frontier is empty, because I wanted to use different data structures for each of the different searches. So for breadth first search, for depth first search, and for iterative deepening, I used the array deck. It's simple because it supports both first in, first out, and last in, first out. So for breadth first search, this one is FIFO, which means that I add to the front and then I remove from the front. For depth first search, this one's last in, first out. So we push at the front of the queue and we pop. So this is pretty simple implementation in here. The greedy best first search and the 2 A-star searches actually use a priority queue. I wanted to use a priority queue because it takes a comparator, which means that every time we add an item to the queue, it uses our comparator function to sort it. So for example, the greedy best first comparator, it compares nodes when they're added based on their h of n, since the greedy best first search sets f of n equal to h of n. And that is the outline of my code. For duplicate states, I used a hash set that I called explore, and it stores integers, and I actually take the puzzle and create an integer representation of it because it's a bit more space efficient than creating or storing the puzzle itself or a node object. And here when I am doing the search, I check this export frontier to see if it contains the child that I'm examining. And then as I go through and check new nodes, I add each one to this explored set, and that's my duplicate state checking.